Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 44, we will learn about sewerage network design, and this is part 1. The different concepts that we will cover are on sewerage network design, catchment or watershed area demarcation, watershed area demarcation using topographic maps, watershed area demarcation using GIS and DEMs, digital elevation models, and node-based geometric method of catchment division. That would be the final topic. So, now that we have learned how to design sewer sections, and also we have learned how to estimate the total stormwater runoff that actually is generated at a particular outlet, or the amount of sewage flow at a particular outlet. So, based on these two sets of values, we can design any kind of sewers, either it's a combined sewer or a separate sewer. So, let us look into now into the sewerage network design process. So, individual sewer we have learned, but now we will design the entire overall network of the entire sewerage network. And similar to water supply network, here also we have to design the entire network, we have to propose certain diameter pipelines and all, and then test if our design is right or not. And then again we have to design the entire network together, because every section is influenced by other sections. So, the first step in the sewerage network design process is to determine the catchments. So, that we will learn in this particular lecture how to determine catchment areas, and particularly for urban areas how to determine that. And we do it using primary surveys, secondary source data is also required, and also we look into the existing plans as well. So, if the area already has got a sewerage network and there is some way of some consideration has been done for catchment determination, so we will look into that. So, existing plans needs to be considered. Then we will form the zones where we will identify location of lifting or pumping stations, particularly the low-lying areas within our catchment, and also we will determine the type of sewer system that we are going to use. So, we have learned about the different types of sewerage networks and the sewerage systems. So, accordingly we have to make our choices. So, once we have decided on the type of sewer system, then we have to decide on the layout of the sewer network. So, first of all, in most cases the sewer will be plotted along the roads, and in very rare cases we will find sewer networks inside the going in a particular plot of land. So, most of the time we will follow the road network, and we need to do certain things when we design the new network or the new layout of the network. One is selection of outlet or disposal point, that means where the final outlet or the sewage comes out. Then prescribing limits of zonal boundaries. So, what would be the overall area that we are serving. Then location of trunk and main sewers. So, first we have to determine along which direction the trunk and main sewers will be laid, and location of pumping stations if necessary. So, these are the first steps that we need to actually do. So, we also need to compute the sewage quantity for each of those particular areas. Like we have a zone boundary, then we have to determine each of those zones, sub zones maybe as well, and within that we need to determine how many people stay there, and accordingly we need to determine the sewage quantity. And once the sewage quantity is known, for design we have to assume certain flow velocities for the sewage pipelines over there, and based on that we have to determine the sewer sections, the grade of sewers, the slope of sewers, as well as what kind of sewer appurtenances are required. Sewer appurtenances are the different kinds of like manholes, then inlets, what kind of culverts, what is required for this particular sewerage network, that also has to be determined. So, when we create this sewerage network, maybe we need to create index plan, which is of 1:2 10,000 or 200,000, or key plan and general layout at scale of 1:10,000 or 20,000, zonal plans for 1:2500 or 5,000, longitudinal sections of sewer at scale of 1:500 or 2500 even, and structural drawings at 1:20 or 50 or 100 and 200. So this is the this kind of scale has to be followed when we create this kind of plans. So in sewerage network design, usually we follow the sewer lines are laid as per the slope and the direction of the ground surface, because we utilize gravity, and also we follow the street networks, and these are connected in a sequence. That means smaller sewers are connected to the higher order sewers, like building sewers are connected to lateral sewers, which is also known as the building connection. That means the connection with the building line with the sewerage pipeline. Then this connect with the branch sewers. There could be more than one. These are the first public sewer lines that are there in the area, and when multiple of these branch sewers are connect, then it becomes a main sewer. These main sewers eventually lead to trunk sewers or interceptor sewers, and finally we have the sewage treatment plant where it goes, all this sewer line goes, and from sewage treatment plant it may go to outfall via another line, or directly from these lines could go to an outfall and we can dispose without treatment. So this is the sequence in which the sewers are laid. So first we need to determine the boundaries of catchment zones and subzones. For that we require topography, land use, road network, administrative boundaries, and so on. So these are the basic information that we require, and trunk and main sewers are located in the valleys. I will explain that later on. So as per the slope map, you will find that at certain parts, the lowest part along that particular slope map, we will have to lay our sewer lines, the main sewer lines, because those are the main lines where all the other branch lines will come and then they will be drained. So sewers encased in concrete or slip pipes are also seen in many cases. So these are basically for protection of pipe or prevention of contamination of water supply. So where water supply and sewerage line goes together, sometimes for protection, we will actually encase those sewer pipelines. So sanitary sewer is mostly laid at the center of the street, which is economical, but sometimes we can lay it on both sides of the street in case the streets are wide enough, and in that case usually we lay it under the footpath, and sometimes it could be within property limits, like as we discussed in simplified sewerage networks in decentralized system, but it's rare. It's not always we do it, and particularly for conventional sewerage system we never do it. And then we have to also decide on the manholes, that is at all sewer intersections where there is change in horizontal direction, major change in slopes, change in size of the sewers at regular intervals, we will provide manholes. So change in direction only and not size, drop of 30 millimeter in the manhole, and change in so when there is change in direction only and not size of sewers, so there is we can do a drop of 20 millimeter in the manhole, and when there is change in size, the crown of inlet and outlet sewers should be kept at the same elevation. So these are the two things that we can also follow. So when we do a sewerage network design, we have to determine this kind of sewer longitudinal sections, as you can see in this particular image. So the crown remains same, that this is the topmost part, the crown remains same at each, these are the manholes, and the subsequent sewers, which are also the bigger sewers, the diameter increases, and you can see their slope is also provided, and the level gradually becomes lower. So the cover, and this is the cover of the sewer pipeline. The cover depends on pipe size and the expected load, traffic or otherwise, and minimum cover of sanitary sewer is given is 1 meter, and for storm drainage system a minimum cover of 0.5 meter is given, but usually it is more than this. And vertical profile of the sewer networks like this one has to be, for the longitudinal sections, has to be done. And then here we mention the datum line of the sewer. That means that what is the datum available, the ground surface level, the manhole locations, the grade of the sewer, the slope of the sewer, the size and material of pipe, and the ground and invert levels. So, what is the invert level for each of the sewers, particularly at the manhole, the incoming invert and the outgoing sewers invert level. So, these are the data that is required. So, whenever we design a sewerage network, we will put this data in the network. In the next lecture, I will show you a delineation of a sewerage network, and I will show you how this kind of information is also recorded. So, manholes, for manholes we need to understand the surface elevation, the elevation of the sewer invert entering and leaving. So, these are the data that is required, and then we have to, once all this data is there, then we have to design the sewer. And to do that, we need to maintain flow velocities, self-cleansing velocity. This we have learnt earlier, and with minimum head loss within available head. So, we usually follow gravity, only a little amount of head is available. So, we should target for minimum head loss. That is why the slope is also very low, and if inadequate head is there, then we have to go for pumping. There is no other alternative, and or we have to use pumping station to lift the sewage and then actually then lift it to higher levels and then actually again continue. And alternative designs may be tested with or without pumping station and associated cost. So, we can design different kind of different diameters of pipeline, different slopes, or with with pumping stations. So, all this could be evaluated and seen, which gives us the least cost. So, trunk sewers of course are of largest diameter. These are first drawn and then the branches are decided. Main sewer is always larger than the connecting branch at any point. So, never a sewer will connect to a main sewer and it would be of bigger size than the main sewer. So, the main sewer has to be always of the maximum size from any connecting sewer up till that point. So, down the line, the upstream the main sewer may be smaller in size, but at the point where a branch line connects, it has to be bigger than the branch line. So, several iterations of the network is designed, like changing of manhole spacing, size and gradients of the sewer, materials and excavation depths are accordingly adjusted. So, several iterations are done of the entire network to decide on the final layout, as well as the cost of the network would be also determined. And as you know that there are several iterations, it is very difficult to do manual computations. So, that is why we are going to use software as well. So, before we even use software, which I will show you in the next lecture, first we need to determine catchment or watershed, and particularly this is important for urban watersheds, right. So, usually the norm, even if we go for a semi-urban or a semi-rural or a little bit larger watershed, we all know that watershed is delineated from basic topographic maps. And this watershed is the area that contributes to the drains of the catchment or the outlet during any rainfall event or storm. That means, a catchment is basically the area which contributes the water during any rainfall event and during from the sewage flow also as well to that particular outlet point that we have considered in our design, or to any kind of inlet point to the sewer. It's the same thing, right. So, in that way we can actually so the determination of this catchment is important, and topographic maps are used to is the main data that we require to delineate this kind of catchments, because topographic maps contain the contour lines, that is from where we can determine slopes. It includes the settlements, the location of settlements, buildings, roads, railroads, pipelines, water bodies, stream network, dams, swamps, wells, forest. All information is available with the topographic maps. But in urban areas, we require further data, more data is required, and in this case primary surveys needs to be done, and particularly this has to be done for if we are proposing some channels, some stormwater channels, or for normal sewerage network channels. In that case, we have to do detailed survey of those alignments as we have discussed earlier. So, in urban areas more detailed surveys are required, whereas in larger areas for larger watersheds we can depend on the topographic map itself. So, usually when we decide on this catchment, GIS is used, Geographic Information System. So, similarly DEMS are used. This is a digital elevation model that is developed for this particular area. and this both GIS and DEMS together are utilized to determine the catchment of a particular area. And not only the catchment, the streamlines, the flow, the streams that is there for that particular area, those are actually determined based on the slopes and the likely the flow channels, both natural has to be, for particularly natural channels, has to be determined using this GIS and DEMs. I will elaborate that. So, first of all, when we demarcate a watershed area using topographic maps, you can see that this is a topographic map, this particular image, and each contour line on the topographic map represents a ground elevation above the mean sea level, and the points along a contour line are at the same elevation. So, that means all the lines that you are seeing over here like this, all these lines are at the same elevation. So, all these lines, as you can continue like this all fall on the same elevation. And this contour interval, that is the difference in elevation between two adjacent contours, that is also given. That is sometimes it is a few meters, sometimes it is maybe 100 meters even. So, usually in flat terrain we have got only a couple of meters of difference between each of these contour lines. It could be even 1 meter as well. A general rule of thumb says that water flow is perpendicular to the contour line, which gives the maximum slope. So, in between two contour lines, like in between this line and this line, water will flow in this direction. So, that is, it flows parallel, it flows at perpendicular to the contour lines, and in case of an isolated hill, water flows down on all sides of the hill. And boundary of a watershed is a line drawn across the contours joining the highest elevation surrounding the basin. So, boundary of a watershed is a line drawn across the contours joining the highest elevation surrounding the basin. So, let us see in this particular area, in this particular map, you can see the contour lines, and this x points are the points which are of highest elevation. How we can determine that? This you can see that there are contour lines, and gradually they are forming concentric circles, and the one and the x is in the smallest circle is marked by S. So, this actually shows us that this is a contour where gradually the contour is going up, and this is the x point. So, similarly we can find this highest points at different areas. So, the first step in watershed area demarcation using topographic map is to first identify the catchment outlet. So, in this particular case, we already have some water body over here, and we assume that this is going to be our catchment outlet. So, this is the first step in determining our watershed. Next is to mark all the high points on both sides of the outlet water course and also at the upstream of the watershed. So, that means on both sides of this outlet, the high points I can see this, these are the high points. Based on the contours, we can identify these high points around this particular outlet, maybe this one as well. Then the third step is to identify both ridges and valleys. Now, what are ridges and valleys? As you can see in this particular image, ridges are represented by U or V-shaped contour lines with their closest end pointing towards lower elevation. So, these are ridge lines, and then this closest, this U or this could be either U or V shaped lines, and their closest end points towards the lower elevation. So, that means that is how we can determine this is a ridge. So, if you can see concentric contour lines, and if based on this particular U's or V's, we can determine which is the highest point and which is the lower point. So, ridges at the highest point, valleys at the lower point. Similarly, valleys are represented by U or V's shaped contour lines with closed end pointing towards the higher elevation. So, in this case, if this is a valley, so closed end will point towards the higher elevation. And as I told you earlier, that all the trunk lines in a particular area, even if it is mostly flat terrain, there will be some contour differences. The trunk lines are laid along the valley like this. So, that is the idea. That means, this is the lowest point along which the trunk lines are taken, and all branches connect to that point. Finally, starting at the outlet over here, connect all the ridges at one side with a line which should cross the contours at right angles, and then across the head of the catchment, and then around the other side to the outlet. So, that means this is the head of the catchment, this is the outlet, and we go at right angles mostly, and then we connect these highest points. We try to follow right angles along the contour lines. This becomes our catchment. So, this is the catchment area for this particular outlet. So, all water that is formed over here, these are the high areas, high points, and this will travel along perpendicular to the catchments, and then they will try to come over here. So, the next step is to determine within this, now that we have understood this is the catchment, next step is to determine how water will flow in the catchment, which would be the channels or stream channels that would be formed naturally, and then how water will eventually come down to the point to this particular outlet. So, that is the step that we have to do. So, in this particular case, we use GIS as well as the digital elevation model. So, these are the two important tools that we require to determine a watershed. So, first of all, we use the ArcGIS. I am demonstrating this using the ArcGIS software, and we first need to open our topographic map in the ArcGIS software, and then we need to georeference the topographic maps and the soil map or land use map, whatever maps we have got along with us. And this georeferencing is basically fitting the map using this latitude, longitude coordinates and a projection system, so that the map represents the surface of the earth and so on, and the distances reflect accurate distances. So, then the next step is to digitize the contours or digitize the topographic map, the administrative boundaries, maybe the location of settlements and so on. Then preparation of digital elevation model. So, digital elevation model are basically maps which has got these points where elevation data is available, and usually these are satellite images where these are obtained from ASTER. This is advanced spaceborne thermal emission radiometer stereoscopy image, or SRT image, that is shuttle radar topography mission. These are foreign satellites or data sources that are there. Then we can also use CartoDM data of 30-meter resolution, which is provided by which is available in India, and 3 versions of this ASTER data is also freely available, of course, but Indian satellites, using that we can generate CartoDM data, and 3 versions of CartoDM are available of different resolutions, and this is available from the Bhuvan website of NRSC, and you can go to this particular link and you can download this CartoDM data for different areas of the or different for this different parts of India and for different places, right. So, we require this digital elevation model data, and using this using the base map that we digitize and prepare and the digital elevation data, we can start our work. So, for this we use the ARC toolbox, like these are the different tools that are there in ArcGIS. There are several toolboxes. So, we use this hydrology toolbox inside the ARC toolboxes, and within hydrology toolbox we have these commands which are basin, fill, flow accumulation, flow direction, flow length, sink, snap pour points, stream length, stream order, stream to feature watershed, and so on. So, these are different options that are available in the hydrology toolbox, which will be utilized to determine the watershed. So, the first step is to determine, once I have got my DM map, GIS map as well as the DM data, the first step is to determine we have to fill the DM, that is create a depressionless DM. A DM data has got elevation data, so it has got a lot of minor depression. Even though in stormwater design, in the last lecture we were talking about initial abstraction, that means water gets stored in the initial depressions, and once it fills up then only it moves out. But to make it simpler, what we do is to determine this movement of water inside a watershed, we first feel that this imperfections in the this thing. So what we do is this, we create a depressionless DM. So these minor depressions are actually removed. So imperfections or sinks are removed from digital elevation model. So sinks are cells within with neighbors at higher elevation and do not have any downward flow path. So if there is a sink in my data, what happens? The software will not be able to determine in which direction water will flow from this point. So if a point is lower than the surrounding areas, the software will get stuck. So that's why the first job is to make it all, the smaller depressions, to make it all flatter. To determine the flow path of every cell in the grid, the step to fill the DM is required. So that means for every cell we determine whatever rainfall falls in that particular area, or if there is water in that area, in which direction water will flow. We need to determine that for every cell. So that's why we need to fill we need to create the depressionless DEM. So we use the fill tool, and over here in our GIS toolbox, this hydrology toolbox. So there is a fill tool over here, and we utilize that, and using that we can modify the digital elevation model. The next step is to use the flow direction tool, and using this flow direction raster generation, a raster image is created. That is, a raster vector file and raster file, where that means in raster images we have got pixels, and that means we create a new image. So creates a flow direction. So this particular step, we create flow direction from each cell to the downslope neighbor or neighbors, and we use several algorithms for this. That means we determine from one cell in which direction flow will happen. So that means the next lower elevation cell in which direction water will travel, and the popular algorithms that are used is D8, multiple flow direction, or D infinity algorithms. Now D8 algorithm, in this algorithm only one direction is considered. That means from one cell the water will flow in only one direction, but in multiple flow direction algorithm we use from one cell the water can flow into multiple directions. So if I have elevation like this, over here, so water from this part can go this side or this side in multiple flow, but in other algorithms only the one with the highest slope that is chosen, and that is where water will follow. So direction of flow determines the ultimate destination of water flowing across the land surface. So that means for this particular digital elevation model, we determine for each cell where the water will go, and that actually shows us that what kind of stream should eventually form. So that you can see in this particular image, these blue dots, this actually shows the flow of water. So how is the D8? So that is the outcome. So let us look at the D8 algorithm. This is a very, very popular algorithm used in many calculations. In later on, when we do for storm this flood planning and all, this D8 algorithm becomes very important. So here you see that D8 or deterministic 8 neighbor algorithm. This is the most popularly used algorithm. This is the most popular flow algorithm. And what it does is this algorithm scans each cell and determines the direction of the steepest slope to an adjacent cell. So these directions are firstly coded. That means for this particular cell, the direction 1, 2, 4, 8, 16, 32, 64, 128 indicates the direction of flow. If it is on the right side, it is 1. If it is diagonally towards right and south, that is 2. If it is towards south, it is 4, and so on. So based on that, 8 possible flows are possible from one cell. From this cell, either I can go in 8 of this direction, flow to only one cell with the steepest slope. So we find that whichever cell has got the steepest slope out of all this, and flow will be determined towards that. And the distance, the slope is distance weighted. That means the one which is near, just like that, in this case we divide by 1, whereas the one which is diagonally placed we divide by √2. So distance weighted drop is calculated by taking the difference in elevation values and dividing by the distance from the center cell, and √2 for the corner cell and 1 for non-corner cells. So suppose these are the elevation data for different cells like 78, 72, 74, 67 and so on. Now let us assume that we have got 69. So the surrounding, this side is not there of course, but surrounding, which one has got the highest slope? Like difference from 69 to 74, 69 to 67, 69 to 53, 69 to 64, 58. So, we find that the difference is most in maybe it is same in 2-3 directions, then we can choose only one. So, let us in this case the difference in 6, 58 to 64, whereas for 64 to 61 the difference is 3, 64 to 68 it is 4, 64 to 69 it is 5, and so on, right. So, this is the highest slope. So, we choose that one, and this is what is shown. So, direction is 1. Similarly, all the directions are computed, and based on that the flow directions are shown in the in this particular map. And this flow direction, when the next step we actually see that how many flows come into this particular point, or how many flows come into this particular point. So, over in this this particular cell, this flow comes, this flow comes. So, there is, and also this flow comes. So, the value of this flow is 3. So, that is 3 given over here. So, in this way we also determine what is the flow accumulation in each of these cells, flow direction as well as flow accumulation. So, in ArcGIS, output of flow direction tool D8 is an integer raster whose values range from 1 to 255. The multiple flow direction algorithm divides the flow from cell to all downslope neighbors, and it divides the flow into as per the slope. So, based on which algorithm you use, you will get different kind of flow patterns. So, in the flow accumulation tool that I just showed in the last image, first of all, we can use a basin tool can be used to determine the catchment areas. This is based on the ridges. What I did in the 2 slides back, that I connected all the topmost points and created the catchment area. So, the basin tool actually does that, and that is, you can see this red boundary as the basin for this particular catchment. And this flow accumulation raster leads to this kind of blue lines. This actually shows the flow of water in this particular catchment. And this is achieved by the D8 algorithm, and this helps in determining the stream network, and the tool calculates the flow into each cell by identifying the upstream cells that flow into each downslope cell based on landscape topography. So, I have already shown that via the algorithm, that we can add up all those directions of flow and then we get a score. So, the important step is a threshold value is given to identify cells with high flows where streams and channels are to be expected. That means, for certain cells we give a threshold value. Okay, like in the previous slide, if I give a threshold value of 7, that means wherever there is 7, we assume that that's the final point where flow is accumulating. So, flow accumulation point, if I make it 1, so all points will look like a stream, like all several in this particular. But if I give the minimum value is 7, then this line, this one will become will be highlighted. So, this will be the direction of the stream, right. So, that, or like this. So, that is why we need to give a threshold value. So, this could be computed using map algebra by doing some basic computations in GIS, that cell values higher than this has to be chosen, and that you can see. So, each cell has got an outlet point or a pour point which shows the location where water would naturally flow out. So, like wherever the water is going out from a particular cell, that is the outlet point or a pour point. So, when we determine then using the pour point tool, we determine the pour points. So, pour points calculate the total contributing water flow to it. So, that means at a particular pour point, we assume that we determine how much water is coming to that pour point from all the surround contributing catchments, and only high flow accumulation areas are considered, otherwise the watershed would be very small, and pour points are sometimes predetermined. Snap pour points tool snaps the pour point choice of user to the nearest high flow accumulation areas within specified distance. So, that means the snap pour point tool is there. So, if I give it somewhere and then use the snap pour point tool, it will actually match it with the actual pour point based on the flow accumulation tool that has calculated, right. So, based on that, one pour point would be considered, and pour point again only high flow accumulation areas are considered, otherwise every point will look like a pour point, right. So, that is why we only choose the higher flow accumulation areas, and we delineate the watershed for each of these pour points Like the watershed tool is based on the output of the snap 4-point tool, and it only selects pixels that contribute to the particular point. So, for this 4-point, whatever area has contributed water, so that becomes the catchment of this particular 4-point. So, that is how we can delineate a particular watershed. So, as you can understand, this kind of delineation is possible when there is lot of change in terrain, there is lot of change in slope, the area is pretty big, then we can find the natural channels and so on. But in urban areas, this is very, very difficult. The slopes are mostly flat, and natural areas, like that, formation of natural channels is very difficult, even though there is a tendency towards that, but usually most of the water comes to the road network because there are roads at certain interval and actually flows along the network. The roads are designed to carry water. So, that is why roads become very, very important. So, there is an alternative way to determine catchments in urban areas, and this is known as node based geometric method of catchment division. So, DM based hydrological method are based on the topography of that particular area, and because these are flat, in case of flat areas like urban areas, this result in lot of parallel pseudo channels. Even though those flows are not available, you will see lot of parallel pseudo channels develop when you do the analysis that we have just done earlier using GIS and DM. So, that will lead to wrong results or wrong kind of flow patterns for a particular urban catchment. So, an alternative way is to delineate catchments or sub-catchments using this node based geometric method, and this is usually done for areas less than 10 square kilometer, which also matches with our the same assumptions as we have done for this using of rational method, that we can use it for catchments of smaller areas. So, similarly, we can determine that particular this particular area of 10 square kilometers could be now broken into smaller sub catchments, and this in this methods nodes are first determined. What are the nodes? These nodes could be major inlet points, it could be junctions points, it could be known points of water stagnation or any other important user defined points. So, in a particular sewage network, this is a junction, or these are along this is the road network. So, these are multiple junctions and these are the inlet points, and then there are manholes as well. So, we can determine that this inlet point is the where water enters in. So, the surrounding area could be the catchment for this particular inlet point. Similarly, for this inlet point, this is the catchment, right? And then we have another road going over here. So, that road would be having a catchment like this. So, we determine the node, and surrounding that node would be the catchment. Now, the best way to go about determining that, as you can see in this particular image, we have determined the nodes, and then we have designed Thiessen polygons or Voronoi diagrams around those particular node. If you remember Thiessen diagrams from our earlier delineation of catchments, particularly for rain gauge stations at the beginning of the course, that we draw perpendicular, we connect all the different nodes, and then we draw perpendicular bisectors, and wherever they connect, they form this hexagon or this polygons, and this becomes the contributing area to this particular node. So, this is a typical geometric way of dividing the catchment. There is no consideration of the actual slope and all, but that is what is required in urban areas, because neither there is slope, neither there are open channels, and existing land use, road network, lake reservoirs and sewer network layers are considered when we decide on the location of these particular nodes, and the final catchment and sub-catchment boundaries are adjusted little bit. And catchment areas are limited to sewer lines along the road and its surroundings in most cases. That means, the sewer line along a road and the surroundings of that particular road, that is the catchment area of this particular sewer line. Sometimes this may be even half of the road. If there is two sewer lines on two sides of the road, half of the road actually contributes to a particular inlet along that particular road. So, the catchment area is that small. So, in some cases, in some urban areas, this node based geometric method is fine, but in some cases this is inadequate, and we use a combination of both the node based method as well as the other method, which is that the DM method, where we delineate or determine the natural stream orders or the natural stream channels. We determine those things, and we can combine both to formulate the final network or sewage network for a particular area. So once we have the catchment and roughly the nodes and all, we can determine what is going to be our sewerage network. So first, that is what we have to determine. So this is called a hybrid catchment demarcation method. So this we will detail out when we will do stormwater planning or stormwater drainage planning. We will look into that, or rather flood planning, we will look into that. So to conclude, catchment area demarcation is done using mainly two methods, that is based on topography and DM, or based on node based geometric method. While the first method is more appropriate for larger catchments, the second method is better for urban catchments with a flat terrain. And however, catchment demarcation is not a straightforward quantitative process, but also requires considerations for land use, road network, administrative boundaries, etc. Usually a hybrid approach combining all the above is considered most appropriate. So these are references you can study. Thank you.